Hello everyone, I'm Giorgio Mangioni. I'm a second year PhD student from Heriot-Watt University, and today I wanted to talk about how to preserve hierarchical hyperbolicity when doing some quotient procedure. What I'm going to talk about is joint work with a bunch of people from two different projects, and so I'm going to shoot out to a thanks to Caroline Abbott, Berline, Thomas Ng, Alex Rasmussen for the first project, and Francesco Fournier-Facio and Alessandro+Sisto, which is also my supervisor for the second one. So, first of all, what is hierarchical hyperbolicity? It's a class of groups, pretty wide. They include mapping class group surfaces, a lot of cubulated groups, a lot of Artin and Coxeter groups, a lot of three manifold groups, and they all come with the property of having some equivalent projection to some hyperbolic spaces, which one can use as coordinates. So they are one big beautiful family of groups, and they enjoy a ton of very beautiful properties, including a very precise Tilts alternative. So every subgroup finally generated is either um, virtually abelian or contains a free group. They have good algorithmic properties. They have very good actions on um, very nice uh, spaces like asymptotically cut zero spaces, which means that the cut zero inequality is satisfied up to a sublinear error in the diameter. Or they have actions on injective vector spaces, so they also enjoy Helly-like properties in a way. And so it is foremost to understand how widespread this property is, because we can't have enough. We need more hierarchical hyperbolic groups. So what I do in my PhD research is to try and understand which kind of quotient procedures preserve hierarchical hyperbolicity, meaning that if you start with a group which is in this big beautiful family and you take a certain quotient, then you hope that the quotient is still in the big beautiful family. So the first quotient I want to talk about is the quotient by random walks. So you start with a finally generated group, any group you like. You take hopefully a finite symmetric generating set, and you define a simple random walk on the group as a sequence of random variables that start from the identity of the group, and at every step you start where you were at the previous step, and you choose at random one of the generators and you move in that direction. So in the picture we have a random walk on z square, for example, with the standard generating set. So you start at the identity, then at time one you choose one of the four adjacent vertices and you move there, then you forget what you did before and you move again, and so on and so forth. And it's possible that you backtrack, of course. But it's important that at every single step you have, like, the random walk at that step is an element of the group. So what you can do is you can take a bunch of random walks, each independent of each other, so they don't know what the other are doing. You let them go for a while, and then you stop them. You take the subgroup they normally generate, and consider the quotient of the group by this subgroup. And we call it a random quotient because what we did was at each step choosing randomly where to go. And so our first theorem is that if you start with the hierarchically hyperbolic group, which is also acylindrical hyperbolic, which is not a restrictive hypothesis actually, then the random quotient, it's still gonna be in the big family, so it's gonna be hierarchically hyperbolic, with probability approaching 1 as t goes to infinity. So the more time you let your random walks go, the more likely it is that you stay in the family when you quotient by these elements. And actually our result recovers, or let's say improves actually, some folklore results which were never actually written, which just talk about relative hyperbolicity actually. So in the same setting, if you have a non-elementary hyperbolic group relative to some collection of peripherals, then a random quotient of this group is going to be, again, non-elementary hyperbolic relative to the same collection of peripherals, with probability approaching 1 as this goes to infinity. And for hyperbolic group, this might follow from a theorem of Delzon, but it was never explicitly written, and it should be completely new for relatively hyperbolic groups. So on the very other side of the spectrum, we have a result concerning quotient by centers of hierarchically hyperbolic groups. So what we prove is that if you have a central extension with kernel Z, and the middle group is a hierarchically hyperbolic group, then the quotient is gonna be hierarchically hyperbolic itself, possibly after passing to a finite ignorance group for, let's say, fine reasons. And so as a corollary, you get that the quotient G, even without passing to a finite ignorance group, is gonna be a hierarchically hyperbolic space, but not necessarily a hierarchically hyperbolic group, meaning that the geometry of the group is the right one, but there are some fine combinatorial properties which are required to be in the big family, which the quotient might not satisfy. But up to a finite index, everything is fine. It's nice that in our proof we prove also this equivalence between the extension being hierarchically hyperbolic and some notion coming from bounded cohomology, which is the fact that the extension is bounded. So we say that an extension of central extension is bounded if you have a retraction from the middle group to the kernel, which is a quasimorphism, which means that it is almost a morphism up to a finite error. Because if you take two elements, then the sum of their image is almost the image of their sum up to a controlled error. And in a way, you should think of this retraction as a way to coarsely split your extension. It's not really splitting algebraically, but at the level of geometry, at least, you have that E is quasi-isometric to the product Z times G, where the map is, well, the quasimorphism for the first coordinate and the projection for the second one. And in a paper of Abbott, Mark Hagen, Harry Petit, and Abdul Zaloom, they proved that if a central extension with the base group being hierarchically hyperbolic is bounded, then E is hierarchically hyperbolic itself. So putting our result and their result together, what we get is that if you have a central extension and you start with the middle group, which is hierarchically hyperbolic, then the extension itself is bounded and G is commensurable to an HHG. So there is this almost rough equivalence between the extension being bounded and the middle group being hierarchically hyperbolic, almost. So with this, I thank you for your attention, and here is the list of papers that I cited, and thank you for your attention again.